Okay, so let's work this problem. So what we have is we have a simple supported beam. This is going to be a roller, and this is going to be a pin support. And you can see I've got a uniform dead load, a single live load, and we're going to want to find the maximum positive moment at C and the maximum positive shear at C. I'm going to do we'll do the moment one first. So the first thing we need to do is find our influence line for the moment at C. So I'm going to use Mueller-Breslau, and I can do it graphically, right? So there's my graph. I'm looking for the moment at C. Let me just bring down a few lines to let you see it. So remember what I'm going to do is I'm going to imagine at C I have what? A hinge. Right? And then I'm going to put positive moment on both the right and the left-hand side. And how will that move? How will this point C move up? Up or down? It will move up. So that means that the shape of the influence line will look like that. And I do have some dimensions here. This is, you can see 1 meter and 3 meters. So really all I need is what is the value right there. So I want the unit load to be at that point. So I'm going to redraw this beam, and I'm going to solve for that one condition. So I have a reaction at A, and I have a reaction at B. So there's my A, Y, B, Y. And I'm going to put my unit load right at C, which is about here. And that would be at 1 meter and 3 meters. And my objective is to find the moment at C, which is right here. So you can imagine that we would probably end up eventually cutting the structure right there. And now you decide, do I want to work the left side or the right side to find the moment at C? You choose. Left. So if I do the left, I need to find AY. So let's do that first. So I will sum moments about B. Make sure it's in equilibrium. So about B, my 1 creates positive moment. Again, it has no dimension. The moment arm is 3 meters. And then AY creates negative moment with the moment arm of 4 meters. So it looks like AY is going to be 3/4. No unit. Okay? That's not too surprising. But then I'm going to come back and I'm going to cut the structure at C. And now we're looking at the moment at C. There's my positive bending moment. Remember, this is 1 meter. And also remember that we just found the reaction. It's 3/4. Can you find the moment at C? Yeah, if you don't see it right away, you can always do this. You can sum moments at the cut. What do we have? Yeah.
Why did you not put a moment at BY?
At BY. There is no moment at BY. This is a pin.
Okay.
If it were fixed, then this would be an indeterminate problem. Yeah. This is one of those ones where I took the example image from the book. And if you actually look at this problem, the author would say, assume B is a pin and A is a roller.
You're going to say that on the exam, right?
Of course. Yes. You will never have to look at this and make a determination. Okay, so the moment at C is positive. The reaction is going to create negative moment, and that'll be a force of 3/4 and a distance of 1 meter. So the moment at C is going to be 3/4 of a meter. or 3/4 meter. So that means all the values on this are in meters, and this becomes 3/4. We just found it. So it took a little bit longer to get the value for the influence line. That's why Mueller-Breslau is called quantitative. You get the shape, but you don't necessarily get the value. You still have to come back over and solve for at least one position to get a value. But anyway, that's a lot better than having to do multiple values for the unit load at various places, and sometimes you get multiple free body diagrams. I don't think that's a pretty simple problem. If I gave you this problem and said, what's the moment at C, and that was your only question for an exam, you should be very happy. Very happy. I hate to make you happy, but you're not going to get that kind of problem. But you would be if you did. So what do we do now? So now we have a full influence line. So the problem says, what's the maximum positive moment at C? We have a moment at C influence line. So looking at the first one, which would be the concentrated load, all right, it's 3 kilonewtons. So where do I put my moving 3 kilonewton load to create the maximum moment at C? At C. So my concentrated load I'll put live. Live usually means it moves. Live load. So that'll be a value of 3 kilonewtons times the maximum ordinate value, which is 3/4 meter. And that's 9 divided by 4, that's 2.5? No, 2 1/4, right? Is that right? 9 divided by 4? 2 1/4?
Yeah.
And that would be kilonewton meter. And I'll put a blue line on there to show you that blue matches that. So the next one we have to do is a uniform dead load. Now how do we do uniform loads? We take the intensity of the load times the area under the curve. So this is going to be a uniform dead load. And it has a value of 500, and that's newtons per meter. I'm going to multiply that times the area of the curve. This curve is a triangle, so it'll be 1/2 the base, which is 4 meters, times the height, which is 3/4 of a meter. Looks like the 4's cancel, and you get 3/2 times that. Looks like 1.5. No, it would be 7. Is that right? No, it'd be 1.5 times 500. Yeah, 750. But in kilonewtons, it would be 0.75 kilonewton meters. Did I do that right? So then you add those two together, so the moment at C max is equal to, you add those two together, in this case it just comes out to be 3 kilonewton meters. There's your final answer. That's the maximum moment at C for a live load that can be any position, and then the dead load, which is going across the whole structure. Any questions about that? So let's do part B, which now wants the shear at C. So now we have to do what? We've got to draw a shear influence line. So let's start all over. I'll draw a template for that. X. There's our ordinate value. That'll be the shear at C. And again, I'll bring down some lines to kind of give us where we're at. Now what are we going to do at C this time is we're going to put that little shearless connector in, right? And then I'm going to put positive shear on this side and positive shear on that side. So looking at this left bit, is this left edge going to go up or down? It's going to go down. So it'd have to rotate something like this. And this left edge of the right side, is it going to go up or down? It's going to go up. So that's the qualitative part. I'm going to redraw it and maybe try to make it a little more to scale. And it should look something like this. Now remember, this is 1 meter, and this is 3 meters. Now we know this change here has to be what? 1. And since this is 3, this height would be proportional to 3. This height would be proportional to 1. So this value here has to be 3 times what this value is here. So 3 plus 1 is 4, so it's quarters. So this should be 3/4, and this should be 1/4. 1/4 is to 1 as 3/4 is to 3. So it's always going to be a function of the dimensions. And you can always go back and check it. 1/4 over 1, is it equal to 3/4 over 3? Yes, it is. Some questions about that? So now we have the influence line, we just answered the problem. The problem says, where do I put, I want the maximum positive shear. So where do I put my 3 kilonewton concentrated live load? Where do I put that to create the maximum positive shear? Well, where's the maximum positive ordinate on the curve? Right there at 3/4. Just to the right of C. You see that? So my concentrated live usually mean moves around, has a value of 3 kilonewtons, and we multiply it by the ordinate value, which is 3/4. Has no unit, right? Shear is a force. Remember, our unit load is dimensionless. So if you add that, that looks very similar to what we got last time, isn't it? That's still 2.25. That's just a coincidence in this problem. And I underlined that in blue. I'll underline this in blue too so you can see the connection. What about the dead load? Well, it's uniform. Dead loads don't move around. They're kind of locked in. So our strategy last time for the dead load, don't forget the dead load value, there it is right there, is we take the intensity of the load times the area under the curve, the whole curve. So again, the intensity, I'm going to go ahead and convert this to kilonewton, so that'd just be 1/2 kilonewton meters. That's the intensity. I want to take the area of this whole curve. So I've got a positive area and I've got a negative area. I'll do them separate. So I'll do each of them separate. They're both triangles though, so they both have the 1/2 factor. And that'll be times, well, the area of the first one, the base is 1 meter and the height is minus 1/4. For the second one, the base of the triangle is 3 meters and the height is 3/4. So what's that going to be equal to? Quarter, 9/4. So this is 9/4 minus 1/4 is 8/4. 8/4 is 2. 2 divided by 2 is 1. You get 1/2. Somebody check that for me, though. My wife tells me my brain is slipping and I can't remember anything, so that's her job.
Whoa.
Yeah.
So can you just reiterate why you keep the negative sign
Which negative sign?
on the 1/4?
Because it's a negative area. This is a negative value. So what's the total? Then so for the shear at C, you just add these two together and you get 2.75 kilonewtons. So that's the maximum shear at C that can be created by this combination. Now, just so you can see this, I think what I'll do real quick is I'll redraw the beam. A was a roller and B was a pin. And the uniform dead load really is applied over the whole beam. So there's the dead load. And then the live load is where? Well, we found it was right here at C. So that means the live load is right there. So that's where my 3 kilonewton force creates the maximum shear at C. And of course my dead load of 1/2 kilonewton meters is applied everywhere. So that's the loading combination that creates the maximum shear at C. We look back to the previous problem. What was different? Well, the dead load is still everywhere. And where do we put the unit load? At C also. So in this particular problem, it's not always like this. The load combination is the same to create the maximum shear and the maximum moment at C. Questions? Should we work more of these? No?
Indeed.
Oh, indeed. Indubitably.